Well, we continue this lecture by knowing or talking about some operations that we can do with power series. All the operations that we are going to do are term by term. So let's see what we can do. We can do a linear combination. So if we have this power series and this other power series with the same center, they might have different coefficients, AM and BM. And if we take two real numbers, alpha and beta, we can take the linear combination of this power series, and what we get is a new power series with the same center and these new coefficients here. Just the linear combination between AM and BM. Okay, then we can differentiate a power series, also term by term. So here we have this term, and when we calculate, when we compute the derivative of this power series, it's just differentiate each of those terms. So as you can see, what we get is this m here, this coefficient is still there, this number, and we get a -1 in the power. And the only thing important to consider is that the original one starts at m equals 0, and then the differentiated one starts at m equals 1. Okay, and maybe you can imagine that if then I compute the second derivative of f, I will start in m equal 2. If I compute the third derivative of f, then the differentiated power series starts at m equal 3, and so on and so on. Okay. Then we also can integrate a power series, again term by term. So we just integrate this term, and the calculation is here. Well, the coefficient am is not there, but it's just a number, and then we multiply by that one. So this is what we get. So if we integrate our power series, we get this +1 in the power, and this other number here. So when we differentiate, we have a -1 and this m here. When we integrate, we have a +1 and this other number here. So everything is done term by term. Okay, example. Again, this power series, 1 plus x squared, and so on and so on. We know that is equal to this function, and we know that this is the interval of convergence of the series, which is centered at a equals 0. Then, if we differentiate this f, what we get is this new expression. When I differentiate 1, I get 0. When I differentiate x, I get 1. X squared, I get 2x, and so on and so on. But since we have the identity, what we get is the expression of the power series of this new function, 1/1 minus x squared. Okay, so this new expression can be written as this new power series. Okay, so maybe this example is not only useful about differentiated power series, it's only useful because if I know certain power series, then I also know the power series of the derivative, which is a new function, and that would be useful in the exercises later on. Okay, so remark. The differentiated series has the same radius of convergence as the original one. And remember this thing that the m where we start the differentiated series changed. Okay, if we differentiate one time, then the starting point is m equal to 1. If we differentiate 2 times, then the starting point is m equal to 2, and so on and so on. Okay. What's next? The identity principle. So if we have two power series and they are equal, well, we have the same center and we have this identity. So this expression with AM is equal to this expression with PM. Then we automatically can conclude that the coefficients AM and Bm are equal for every m. That also will be super useful when we are applying this power series method to solve ordinary differential equations. Okay, what's next? Composition of power series. So let's see this composition of power series with examples. First one, famous series. Already in the I think this is the third time we use this power series in examples. So this is quite a nice power series to work with. Okay, so here we have this expression, and we know that this is equal to this function when x is between -1 and 1. So if we take an x there, then minus x also belongs there. So we can compute f in minus x, which just means that we can replace this x, but minus x, and we get this new expression, this new power series here, that we can also put here, that this is equal, since we have this expression, so we can also say here that this is 1 over 1 minus x, which is 1 over 1 plus x. Okay. Second example. So by composition of power series, we mean we know the power series of a certain function, and then we can evaluate that power series in certain point, in certain expression, let's say, depending on x, so certain function, to get a new power series. And then, as you see, now we know the power series representation of this function, 1 over 1 plus x. Okay, second example, the exponential, that you can find this expression, for instance, using the Taylor series representation. So you compute the derivative of the exponential and evaluate that at 0, and you will get this power series. So we can compute this power series in, for instance, x squared, which is just replacing the x by x squared, and we get this new expression, which again we can add here, that this is equal, since we know that f of x is this function, this is equal to the exponential x squared. Okay. So that was composition of power series. Let's continue with shifting indices. We have here this expression. So we have two power series, not exactly written as power series in the sense that if we look at the power, here is m minus 1 and m plus 1, and we want to have this expression written only in terms of x to the power m. Okay, so we are going to shift the indices in such a way that we have this power. How can we do that? And then we want to write this expression, this whole expression, as a single power series. Okay, so let's start with the first term. Also observe that here we start at m, the power series starts at m equal 1, and here the power series starts at m equal 0. Okay, so let's start with the first term here. We don't want this m minus 1, so we call it n. And what we can say is that, okay, m takes the values 1, 2, 3, and so on. So m minus 1, which is n, will take the values 0, 1, 2, and so on. So that's why we have n equals 0 here. And we want to rewrite this in terms of n. So we have this identity coming from this identity that we forced. So we call n equal m minus 1. So this m now is n plus 1. And since we call this n, here we have n. Okay, and now just we change the n for an m, so we have always the parameter m in the index set. So we get this expression that now is a power series, since here we have an m. Okay, we want to write everything in terms of x to the power m. So we have the first term of the expression already done. Let's see what happened with the second one, which was this one. So we don't want this m plus 1, so we call it n, k, any letter you want, just other letter. And we okay, so now m takes the values 0, 1, 2, and so on. So n, which is m plus 1, will take the values 1, 2, 3, and so on. So here there is n, maybe it's not clear, it's n equal 1. So we start in n equal 1. And now this m plus 1 turns into an n. And again, we just recall here m instead of, recover the m instead of n. So we have everything written in terms of m. Okay, so going back to our expression here, we did first the first term, then the second term. What we get is this other expression, and now we have to pay attention because, okay, we have this power xm as we want it, but here we start at 0 and here we start at m equal 1. So what we do in the final step to try to get one single power series expression is, okay, I just split this one in this way. We put here the term with m equals 0. So here you can see, here you can see when m is equal to 0, we have 0 plus 1 x to the power 0. And then we have the rest of the terms, right? From 1 to 1, 2, 3, and so on. So let's say that this expression comes from here. This is this power series that we just split the terms. We separated the term with m equal to 0 and the rest. And why we did that? Because now, well, here is just a 1, which is here. And then we can add these two power series because they start at the same index. So and we use the property of that we have a linear combination, so we sum this just term by term, which means this m plus 1 plus these 2 term by term. That's why we have here this m plus 3. And that's all we can do to write this expression as a single power series. Okay, so in this exercise we use these properties of how to operate with power series, which is term by term, and the very important property of how to shift indexes, so in such a way that we can rewrite an expression to get a single power series, everything depending in the power m. Okay, let's see. Remember that we are studying these power series properties and power series in general to solve linear ODEs with non-constant coefficients in the ODE. So we are interested in combining these power series properties and the derivative of this power series. So let's see an example. How to use and combine this operation of how to operate with power series and derivatives and so on, towards to use them to solve ordinary differential equations. Okay, so assume we have a function ux that admits this power series representation with certain radius of convergence positive, and we want to find the expression, the power series representation of this quantity, which involves not only the function u, but also its derivative, and also, well, these functions. So imagine that if this in the future becomes part of an ordinary differential equation, then this ordinary differential equation would be a linear ODE with non-constant coefficient. Okay, this 2 is a constant, but for instance, this coefficient is clearly not constant because this variable x is there. So we won't be able to use the method that we learned in lecture 1, which was the characteristic equation method. That's why we now are seeing this power series method. We are going to see this power series method to solve this type of ODEs. Okay, so far this is an expression, it's not an ODE, so we are going to find the power series representation of this expression. Okay, so we can split this in a couple of steps. So first, given the u as a power series, we can compute u prime, and after that, as we did in the previous exercise, try to write the whole expression as a single power series using these linear combination properties, the shifting indices properties, how to shift indices, and so on. So that would be our 2 steps, let's say. Okay, so here is u, and here is u prime. Remember that we differentiate term by term, so we get this minus here, minus 1, sorry, starting in m equal 1, this m here. Okay, now we try to work with this expression a little bit before shifting indices, because now we can see, maybe it's time to shift indices here because this is not written with x to the power m. Okay, it's true, but we also have to compute this distributive, this multiplication that we have here. So we first do some calculations. We distribute that 1 plus x there. So we get 1 times this power series, which is here, and x times this power series, which is here, and this one we just copy it here. Okay, But now, this x here with this x to the power m minus 1 turns into x to the power m, which is nice because we already have a nice expression in terms of x to the power m. So, and remember that here we are starting in m equal 1 and here in m equal 0. Okay. Let's continue. Here we are. As we said, this is nice because we already have the x power m, so those are the nice terms. But this one has the x m minus 1, so it's so far a bad term. But we can shift the indices to get what we want, which is the power x m. Okay, so we rewrite this as we were doing in the previous exercise. We call n or k or the letter you want equal m minus 1, and we check which values takes this new parameter n. So since m takes the values 1, 2, 3, then n, which is m minus 1, takes the value 0, 1, 2, and so on. So what we get is that this series can be written in this way, and then again we rename n equal m, so we have everything in terms of the letter m. Okay, remember that this m, we look at this equation, so m will be n plus 1, that's why we have this n plus 1 here. And remember also to change this this m there in the coefficient. Okay, so going back to the expression. Now we have everything in terms of x to the power m, which is quite nice. And we have to check if we can sum term by term, which we can do, but we have to pay attention to where each of these series starts. So let's say that these two are nice because they start in the same m equal to 0, and this one starts in m equals to 1. But that's not a problem. We are going to split this series in such a way that we can get a single power series at the end. So, in principle, here, it's clear that we are starting in m equal 1, but look at this m. It's multiplying this am. So, if we add here the 0, doesn't change. It doesn't change the expression because 0 times am is still 0, so we have exactly the same power series. So we do this trick, just noticing that if we add 0 here, nothing changes, so we can do that. And then we have x to the power m every time, and we start in the same m, so we can sum these term by term. So we have this term here, this term here, and finally this minus 2 am here. So these are the same coefficients am, so we can put them together and we get this expression. So maybe it was a bit long, but not so hard if we remember how to use this power series property. So what did we use here? We use a lot the shifting property. how to differentiate power series with this term by term. So we operate power series term by term. That's also very important. Here, remember that first we need to work a little bit in the expression before really shifting the indexes, because maybe then once we work with the expression, then we have maybe to shift the indices again, and so that would be twice the work. And then once we have the expression written with powers xm, we check where each term starts, and then if we have the same starting point, the same starting m, we can just sum term by term, and we get the final power series expression. Okay, so let's stop here, and in the next piece of the lecture 2, we will see finally the power series method to solve ordinary differential equations with non-constant coefficients.